Hi, everybody. Welcome back to another lecture of artificial intelligence. So now I also know why I was coughing so much last week. Actually, I had Corona, but I'm almost recovered. My wife also had it then, but we're both good. And so that's the benefit of the online lecture. I can just continue, even though I would have now I cannot infect anybody, but if I would have done it in person, it would not have been optimal, of course. Okay. So what have we discussed last week? We discussed utility functions, preferences. We discussed decision trees and also the value of information. And there was one thing that was remaining, and that were decision networks. So we're looking at decision networks because these scale much better than decision trees. So if you have a decision tree, then the number of branches grows exponentially with the number of decisions, and you don't have this issue with decision trees. Decision trees are also often referred to as influence diagrams in the literature. And talking about literature, decision networks are not treated particularly well in the AI book. That's why we're also using some aspects from other textbooks that I mentioned at the beginning of the lecture. Good. So as I mentioned, decision trees can be very large, and the idea is to make use of conditional independence, as we have already done for Bayesian networks. So if you remember, if you would create a gigantic table for all the joint probabilities, then the number of entries for the table would have also been exponential in the number of random variables. But by using conditional independence in Bayesian networks, we were able to also very concisely present problems and solve problems regarding probabilistic inference. And so the solution now is to take a Bayesian network and add two more ingredients. So the ingredient that we keep from Bayesian networks are the random variables. So if you remember the garden party example that we discussed last week, we had a random variable which was rain. So there was a 60% that it rains and 40% that it didn't rain. And as a decision, we had to make the decision whether we will invite people to the party or not. And then there were different utilities. So decisions are then denoted by this rectangle, and utilities by this diamond. So in this lecture, we assume without loss of any generality, there's just one utility node, but you can also draw a decision that works with more than one utility node, but it's not really required. Okay, so that's what I just mentioned. So now, as for Bayesian networks, we can now indicate that a random variable x is conditionally depends on the random variable y. So once we know y, we also know x. And but we don't only have links from a random variable to another random variable, but also from decision nodes to random variables, as shown here. So then the meaning is that after we made the decision D, then we reveal the value of x, and the value of x, of course, will depend on the decision that we've made. And of course, it can also, random variable x can also depend on the decision and also on another random variable at the same time. Good. Then there are also links to utility nodes, and these links can come also from decision variables and also from random variables, as shown here. So also there can be more than one decision variable or more than one random variable influencing the utility node, as we'll also see in a medical example later in this lecture. Good. You also have the opposite direction, that you have a link from a random variable to a decision variable, and that simply means that the state or the value of the random variable x will be known before we make the decision D. And also it can be that the decision variable is influenced by another decision variable. So that means that decision small d is taken before decision capital D is taken. And also both at the same time are possible, so you can have links to a decision node from a random variable and a decision variable, or also several random or decision variables. And also let's come back to this oil drilling example. So now this is drawn down here is a decision network, where first we have to make a decision whether we test the drilling site or not. So whether we send a seismologist there, and then the seismologist will tell with what probability he or she believes that there's oil. And then we make the decision whether to drill or not. And of course, the testing will influence the utility, because testing costs money. So this reduces the utility. However, it increases the chance of finding oil, and that, of course, increases the utility. So we have to find an optimal trade-off, and this optimal trade-off can be quantified using the value of information, as we've seen in the last week when we started this lecture. And of course, why do we have oil and seismic as a random variable? Because the seismologists don't work perfectly, so there are false positive and false negative cases. So it could be there is oil, and with a small probability, the seismologist says no, there's no oil, or there's no oil and the seismologist says there is oil. Similarly to a corona test, is also not a perfect test. Okay, so that's all what I said, just written here. Good. So an important aspect of this decision networks is that we have some partial ordering of decisions and random variables that are revealed. So we usually, first we have some random variable that is revealed, then we make decision D1, then another random variable or a set of random variables is revealed, then we make a set of decisions and so on. And yeah, so it just means that xk are the variables revealed before decisions dk and dk plus 1 are made, and so on. And you can, as I said, it can be a set of decisions or a set of variables. Good. So how do we then find this partial order? So in the oil drilling example, we would start with the first decision, which would be whether we perform the test or not. And then after that, we have to reveal the random variables that will be revealed after this decision. In the oil drilling example, this was the seismic. So whether the seismic random variable, so whether the seismologist says there is oil or not. And then we will make another decision whether we will drill or not. And at the very end, we add in the partial order all the random variables that are remaining, and that would be oil in our case. So first test, then seismic, then drill, and then we reveal any unrevealed variables at the end of the ordering, which is oil in our case. Okay, there's one more thing is, of course, the decision of drilling will also depend on whether we have made a decision for or against testing. But we will not draw arrows between every possible node, because then you have a fully connected graph, which would be not very easy to read. So what we will assume is that we have this no forgetting assumption. So if test has been revealed, then this will be available in the following nodes. Like if you follow these arrows, so the previous decisions and the previous revealed random variables will be known for each subsequent node. That's why, for instance, there is no arrow from test to drill. So this is this fundamental information link. So an information link is fundamental. If its removal would change the partial ordering, and because of the no forgetting assumption, all the past decisions are revealed that have and revealed variables are available at the current decision, and that's why we only have to draw the fundamental information links and not the non-fundamental information links like this green one here. So this is a more complicated decision network for aortic coarctation. So this is basically, the aorta is basically one of your main vessels going away from your heart. And basically, if you have aortic coarctation, that means this kind of vessel is a little bit clogged. And of course, like now you have a complicated decision network where you have, for instance, age, and age influences how likely it is to have heart failure. And then there are several medical conditions that you can have, which will influence the decision for or against the treatment of this disease. And this treatment will have intermediate results or late results, and also effects on other parts of your body. And all these will then influence the utility that are for or against treatment. So here in the utility has one decision variable and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, no 9 a random variable influencing it. Yeah. Good. So now the question is, how do we evaluate such a decision network, right? So this is not that trivial. And one, what would be a brute force way to evaluate such a decision network if you don't care about efficiency? This maybe someone has an idea, and if you like, you can write it in the chat. Okay, convert it to a tree. Yes, we could convert it to a decision tree. That's a good idea. And then evaluate the decision tree, which creates a rather huge decision tree, but that's a possible way. That's a good idea. Yes, we could try all possible combinations. Maybe I would say that's yeah, equivalent to drawing the decision tree. So yeah, that is already a good idea. Another idea would be, if you're not interested in the exact solution, is to simply perform Monte Carlo simulations. So where we just randomly create values of the random variables, and then create a utility for the sample for when we decide for or against the treatment. And then we aggregate all these partial results from all the samples, which are weighted by the probability of the samples. And then we could also estimate the utility for or against treatment. So that would be another option. Okay, so now we follow a little bit of a different idea, which I'm going to explain now step by step. So in the end, what we have to do is we have to find a decision that maximizes the expected utility. So basically, we have some evidence, and the expected utility depends then on the decision and the evidence that we have. And we call the optimal decision the policy given the evidence that we have. So policy will be also a big topic in the next lecture that we will start in a few minutes. But there we will then talk about policies of dynamical systems where the state changes over time. Good. So what we always have is that because of the partial ordering, when we make decision di, we already know the decisions 1 to I minus 1 and all the chance nodes or random variables from 1 to I minus 1. So then the evidence basically can be composed of all the revealed random variables and all the revealed decisions. And then we want to maximize the expected utility of the decision given all the previous decisions and the previous random variables. And as you know from equation 7, and I can briefly go back if you don't remember. I mean, you probably remember the equation, but not exactly what was equation 7. So the expected utility of x given y can be computed by multiplying the conditional probabilities of x and z given y with the utilities, and then we sum over all the hidden variables set here. And something similar is done here. Sorry, that was too fast. So we sum over all decisions di, and we have here the probabilities of x and d, which can be written as the result of d equals x in our case, given the previous random variables and decisions, then multiplied with the utility. So we are summing over all the xi's here, so that we just then have the utility of the decision given all the random variables and decision variables. Okay, and yeah, so we refer then to pi star as the optimal policy for the decision variable di. Okay, so the only thing that we have to do now is that here we just thought about making one decision. Now we have to make several decisions, and these decisions will be made sequentially from the last to the first decision. And you will see why we go from the last to the first decision in a minute. So before we do that, just we briefly discuss how we can compute the joint probability of all random variables and decision variables. Because the decision variables are not really random, so we made a precise decision. This joint probability is the same as writing it as a conditional probability for the random variables given the decisions, because the probabilities of the decisions are 1, so we made the decisions. And then you can simply use the chain rule, where you always take the probability of xi given the previous random variables and the previous decisions, and then multiply that with the next previous one and the next previous one, and so on. So we will use this now in the formula for the maximum expected utility. So the maximum expected utility over all decisions is obtained by first making the last decision, then we get an optimal policy, then we make the next decision, and so on until the very first decision. So we always want to maximize the utility, of course, and then we start with the last and go to the first one. And as you know, expected utility is by summing over all outcomes, and we are weighing the utilities with the different probabilities. Now we simply replace this joint probability with the formula 9. And what we then do is that we will rewrite this formula for the maximum expected utility by looking at the last decision. And if you maximize the utility for the last decision, then it's like you get a new value, and this can be interpreted as a new utility value for a reduced problem where you only have to deal with decision 1 up to n-1. Because the last decision has already been made, we can compute this kind of new utility, utilde, and then it's like a new problem with just one decision variable left, and then we repeat this over and over again. And then we, in the end, obtain this optimal decision sequence. Good, just one last thing, and then you can always think of questions you might have. So the thing that is a little bit inconvenient here is that we were summing over all states x. However, some states have nothing to do with the decision dn, and you don't have to consider those. So we will split the utilities into utility ua and the utility ub, whereas utility ua doesn't have any dependence with this variable xn. So only with variable xn, x1 up to n-1, and all the cases where xn plays a role are collected in utility ub. And this has the advantage that if I go back now, we compute the sum, we can exclude ua and only have to consider ub, which saves computation time. So ua is excluded, and then we just need to find the best decision given the utilities that really matter. So where xn actually is present, and if xn is not present, then we can exclude this. Okay, so this the theory. Then we will have an example, but before we start with the example, are there any questions regarding this basic principle?
I think you could probably explain the formulas on the last slides a bit more, a bit slower, probably.
This slide, okay.
Probably starting if you go back a few slides.
Also, I should go
probably
back.
Probably this one, yeah. Just judging from the tweetback.
Okay.
Messages currently.
Yes. So expected utility, as you remember, is multiplying the probability with the corresponding utilities, and then we are summing over all possible outcomes. So this is always the core of any formula for expected utilities. And what we want to do now is we want to maximize these expected utilities. And what we can do is we can make decisions, right? And we first maximize the utility for the last decision. And the reason, as I will repeat, is that if we start with the last decision, we can rewrite this as a different utility value. And then we can kind of, by divide and conquer approach, start with the last decision, then repeat this with, again, the remaining decision problem has a next last decision and the next last decision and so on. And then step by step, we compute the best decision for each remaining problem. And as a result, then you will have the best, or the sequence of optimal decision sequence. Or let's say the optimal policy, you don't compute exactly the sequence, because the sequence will depend also on what random variables will be revealed, but you will always have the best policy given the revealed random variables. So that was what we discussed here, that essentially you want to have a policy that, given previous decisions and previous values, what is then the next optimal decision? And this best next optimal decision, of course, has to be, these policies have to be computed sequentially, starting from the last decision to the first decision. So here what we did is we just replaced the joint probability with this formula coming from the chain rule. And so what we just did is we looked at the last case when we maximized dn, and this, yeah, we kind of separated it from the remaining formula. And yeah, one thing what is important is that here we have all the variables from so we have all the variables from I equals 1 to n, which are still here, but when we make the last decision, the remaining variables for the other decisions don't go from 1 to n, the index, but only to n minus 1, because as we know from the partial ordering, that if you make decision dn, only xn is affected, and the other variables, for decision dn minus 1, you don't need xn. Okay. I mean, that is essentially the main formula. And the last part, when you make the decision for decision variable n, it's just like a summation of probabilities multiplied with utilities, which is nothing else than the optimal utility given this optimal decision dn. And this can be viewed as a utility variable of a remaining decision problem where the last decision has already been made. And this is the remaining part of the decision problem that we then have to, yeah, step by step reduce. So from n to n minus 1 up to decision di, sorry, d1. Okay, and that is really a simple thing. So the utility function is usually a complicated function, and some parts or some terms of the function do not depend on xn, and these parts are put then into the part UA, and the other parts where xn is relevant is then part in the utility UB. And because we are summing here over all xn, if xn isn't present, we can exclude it from the computation here, because dn only has an effect on xn. If xn doesn't play a role for the utility, we can just remove the utility and keep it for the other decisions. So that's done here, and then we only have to find the optimal decision given UB, and UA, as I said, is not relevant. This is just, I mean, you don't need this, it just saves you computation time. Okay, so maybe let's look at the example now. Then maybe things become a little bit clearer. So you want to buy your car for your business. Maybe you have a delivery business and it's better, or you might be faster than by car than compared to delivering it by bicycle. However, of course, in inner city areas, bicycle is more economically friendly and even faster in many cases. But for your business, because maybe you have to carry a lot of heavy stuff, a car is better. And you don't want to spend a lot of money, so you go to a used car dealer which doesn't have the best cars, so the probability that your car is a lemon, so a bad car, is 50%. And to avoid this, you can also request a report. So you can make a decision for a checkup where an expert looks at a car and tells you whether it's a good or a bad car. And this costs, of course, some money. And based on this report, then you can make a decision whether to buy the car or not. And of course, the utility depends on whether the car is a lemon or not. If it's a good car, you have a higher utility compared to a bad car. The checkup has an influence on the utility because it costs some money. And buying also has an effect on the utility, because if you don't buy a car at all, you have a not so good utility because you cannot transport many things. If you buy the car, you have a high utility. But when you buy, of course, it depends on whether it's a good or bad car. So here's the table. You have a lemon and you bought a car, so you spend money but have not a good car, then you have utility of -600. If you bought a car but it's not a lemon, then you have a very good utility of +1000. And if you don't buy the car because your business is not working so well, you don't have a utility of -400. And regarding the report, so the expert would tell you it's a good car with 20% probability, although it's a lemon, and with 80% that it's a bad car if it is a lemon. And with 90%, he or she would tell you it's good if it's not a lemon, and it's bad if it is a lemon. No, sorry, if it would tell you with 90% that it's not a lemon if it's if it's not a lemon, that is a good car, and with 10% that it is bad, although it is not a lemon. And of course, if you don't have do any checkup, the report will be, you will not receive any report with probability 1. Okay, so now we go from the last decision to the first decision, and we have only 2 decisions: to make a checkup or not, or to buy the car or not. And there could also be an arrow from checkup to buy. Why don't we have an arrow here? Who remembers? If you like, you can write it in the chat. Yeah, we have this no forgetting rule, exactly. So this is not a fundamental information link. Okay, so the last decision is, should we buy the car? So we want to have the expected utility of buying the car given the checkup and the report. And using formula 7 from slide 7, so I just showed this already today, we can just sum over all values L and use this probabilities multiplied with these utilities and then obtain this expected utility here. The thing is that the probability of lemon and buying the car given checkup and report is the same of just whether it's a lemon or not given checkup and report, because whether we buy the car or not is the decision variable, and that is a decision whether we will buy it or not buy it. So this is something that will be fixed, and that's why it has no influence here on the probability. And also, the utility of buying lemon, checkup and report combined is just the utility of buying and lemon. The checkup is handled by -50 if we perform a checkup, and we don't do anything if we don't do any checkup. And of course, the report itself has no influence on the utility, as we already discussed. So the utility is fully specified by whether we buy the car or not and whether it's a lemon or not. And as I said, the checkup would just reduce the utility by -50 because it costs 50 euros to do the checkup. Okay, so now we have to compute all the cases. So the case could be we perform the checkup and the report is good. So we want to have here this conditional probability of L given C and R, which can be obtained by normalizing the joint probability as we know from previous lectures. And now we can use the same concept from Bayesian networks. So the joint probability of L, C, and good, or of L, C, and report is first the probability of lemon. Lemon doesn't have any parent, multiplied with the probability of report given the parents of report, and the parents of report are lemon and checkup. So it's exactly the same technique we have used for Bayesian networks, where we multiplied the probability, so the conditional probabilities, and we always used in the condition the parents of the network. Okay, and yes, so then we just insert the values for both cases. So for the case that it is a lemon and for the case that it's not a lemon. So this is the case it's not for not a lemon. That's the case. No, that's the case for lemon. That's the case for not lemon. Then we normalize it, and then we know that with 80% it's a lemon, given that the report says good and we perform the checkup, and 82% that it's not a lemon, given the check that we perform the checkup and report says it's good. And in equally or analogously, we do this for the other cases where we get, of course, different probabilities. Of course, the case when we don't do any checkup is easy because we already know that with 50% it's a lemon or not. So this is the easy case here, the last one. Okay, so now we just computed here the conditional probabilities in order to make the decision whether to buy the car or not. We then have to obtain the expected utilities given the decision we buy the car or given the decision we don't buy the car. So we have to multiply the probabilities with the utilities. First, we look at the situation where we perform the checkup and the report is good. And because we perform the checkup, we have to subtract 50 for the cost of the checkup. And we use the conditional probabilities from the previous slide, and the utilities were listed here in this list. And then we see, okay, if we buy the car, the utility is 262 if the report is good. If we don't buy the car and the report is good, then the utility is minus 450. So obviously, the optimal policy, if we do a checkup and the report says it's a good car, is that we buy the car because the utility is higher, and this also makes sense. It's if you have an expert and the expert tells you it's a good car, usually it makes sense if you already paid the money for the report to also buy the car. I mean, it could be that the expert is really not an expert and always tells you the opposite of what is true. Then of course the policy would be different, the optimal one. But here, as you have seen in the probabilities, the probability of a false positive and false negative report are quite small. Good. So now also we do exactly the same for the other case. So the report is bad. And then, of course, in this case, the utility for which is better is the one where we don't buy the car. It's not much difference, interestingly, but there's a small preference to not buying the car. And if you don't perform any checkup, of course, we don't get any report. And then expected utility for buying the car is 200, and expected utility for not buying the car is minus 400. This can be easily seen because no matter what we do, so if you don't buy the car, whether it's a lemon or not, the utility is always minus 400. So that's obvious. And then the utility, if we don't do the checkup, would be, for buying the car is 200, because if it's a 50% chance that it's a lemon and a 50% that it's not a lemon if we buy it. So 50% times minus 600 is minus 400. And this would be 50% of 1000 would be 500, and minus 400 plus 500 would be, we have 200. Yeah, we have minus 300 and plus 500. So if we add these values, you get 200. Again, if you don't have the checkup, then it's always easy to compute in this example. So then the optimal policy would be to buy the car if you don't do any checkup. Okay, so this was the last decision. Now we go to the first decision, whether we want to do the checkup or not. Here we use equation 6 from slide 7. Again, what was this equation? So the expected utility of X is computed by multiplying the probabilities with the utilities and summing over all values Y. So this is, we do this in a similar way now for the first decision. So we want to have the expected utility of buying the car and the checkup. Whether we buy the car or not is determined by the optimal policy of the previous decision. So pi star of B given C and R is what we computed in the previous step. So whether we buy the car or not, given the checkup and report. And now we're summing not over one variable, but over R and L. And because of that, we will remove R and L from the expected utility, and then only obtain the expected utility of buying given checkup. Then there are some other simplifications. So first of all, because the policy is given from the previous decision, this has no influence on the probability. And R, L, and C, the joint probability is the same as the probability of R and L given C, because C is a decision variable, whether we perform the checker or not. This is the same argument that we used here, where we said, okay, the joint probability is the same as the conditional probability because the decision is certain. So the probability here is 1 of the decision. Okay, that's one thing. And the other thing is that the probability of R and L given C can be computed as the probability of R given L and C multiplied with the probability of L given C. So this is just the chain rule again. And that we need to do this, of course, because this probability is not given, but we know probability of R given LC and the probability of L given C from our table here. And then finally, the utility, of course, depends on if you make it as general as possible. In theory, would depend on buying, report, lemon, and checkup. But of course, the checkup is a decision. So, but we know from the table that it's just depends on buying and lemon, and -50 for checkup. That is given. So here we also have some simplification. And there are two possible values now for R and two possible values for L. So we use this table to look at all combinations. So good and lemon, bad and lemon, good and not lemon, bad and not lemon. Then we compute a probability of R and L given C using the chain rule here. And this here just is a reminder of what was the optimal policy from the previous slide. So if we have good report and it's a lemon, then we should buy. If it's a bad, sorry. So we should buy it if we do it a checkup and the report is good, and we should not buy it if the report is bad. We should also buy it if we don't do the if it's the report is good. Yeah, I mean, this is a repetition. So if the report is good, we buy it. If the report is bad, we don't buy it. So that's repeated here. And sorry for that confusion. And then we take the utilities from the table, this table here. And if we do the checkup, we subtract 50 additionally. And because these are only cases with checkup, we always subtract 50. And then for all these four combinations, we now compute the expected utility using the combinations of this table here. So we have the probability of 0.1 times -650, 0.4 times -450, minus 0.45 times this, and this probability times this. And then we end up with the expected utility of 160. If you don't do the checkup, it's easier. The probability of a lemon is 50%, and the utility is -600. And the other way around is 0.5 times 1000 is 200. So overall, sorry, is 500. So overall, we have 200. So this is exactly the value that we already computed here of buying and no checkup. Okay. So now we have the two utilities, one for checkup, one for not checkup. And you can see that the utility for not checkup is better. So overall, the decision we should make is that we don't do any checkup.
Yeah. I think you could return to the previous slide, maybe explain a bit more closely. There was one question: why is good L the same as good not L?
Sorry, which case?
Not sure exactly where.
So was it here, something here?
I think for our next slide, there were quite a few questions. Maybe you could do it again.
So this slide, or?
Yeah, I think this one.
Okay. I mean, this is actually basically the same as evaluating a Bayesian network, right? So we have to compute the probability of L given C and R. And as you know from Bayesian networks, this can be done by normalizing the joint distribution. And how is the joint distribution computed? We look at one, like the first random variable, lemon. This has no parents, so we just use P of L multiplied with P of R, but report depends on checkup and buy. sorry, checkup and lemon. So then here we have P of R given L and C. And if you multiply this, that's equivalent to having the joint distribution. So this is exactly as for Bayesian networks. And we have to compute, because we have to sum over all else, we have to compute for the case that it is a lemon and for the case that it's not a lemon, and then afterwards normalize the results. And then we get these probabilities, 18% and 82%. We do the same for the other combinations, that we have perform a checkup and the report is bad, or that we don't perform the checkup, and then of course we don't have to look into a good or bad report, because if we don't do the checkup, there is no report. So that's actually a rather easy slide, I would say.
I think slides 57, 58 next to you, I guess.
Okay, and this essence of slide 57 was, so on this slide we derived the overall formula and then computed these probabilities here. So now what remains is that these probabilities are multiplied with the utilities and summed over all cases, so lemon and not lemon. So here we have the probability from the previous slide multiplied with the corresponding utility, plus the other case that is not a lemon, multiplied again with the corresponding utility. And then we get the expected utility for buying the car, given that we perform the checkup and the report is good. And here we have the expected utility for not buying the car, that we perform the checkup and the report is good. And of course, the utility for buying the car here is better because the checkup was positive. So then the optimal policy is here to buy the car if we have a checkup and the report is good. And then we do the same thing for the other cases. And here we see that the optimal policy is to not buy the car when we perform a checkup and the report is bad. And the optimal decision, or the optimal policy, if you don't do a checkup and the report is none, of course, that's the only outcome, is to buy the car, because buying has a utility of 200 and not buying has a utility of minus 400 here. So that's all we're doing here on this slide. I mean, we just use ... here because it's always the same formula, and wouldn't see the wood out of all the trees. It's like the German saying, "The Wald vor lauter Bäumen sehen." I don't know what the corresponding English saying is, but yeah, so that's why we only showed to you here in detail how it's done, and then here we said, okay, just do the same way, and these are the numbers. Okay, so the interesting thing is, in this example, not doing the checkup is better, just buy the car. And the value, so the question is now, what is the value of information? And so how expensive should the checkup be so that it's actually worth it? And if you remember, the value of information was defined as the expected utility given the information, so whether it's a good or bad car according to the expert, at no cost. So we don't pay the expert at all. So the way, instead of using this complicated formula, what we can do is we can just say, okay, we take the expected utility of the checkup, which we computed here, and we just say, and we just add 50 euros because that was removed here because of the cost of the checkup. But as I said, in value of information is computed by the expected utility given the information at no cost. So we can add plus 50 minus expected utility without this additional information. So whether the report is good or bad, we don't know here. And that is then the expected utility when we don't do the checkup. And the value here was 200. So now we just have 160 plus 50 is 210 minus 200. So then we can directly compute the value of information to be 10 euros. So if the report would be less than 10 euros, it would be better to do the checkup. If it's more expensive, then it would be better to not do the checkup. So this is kind of a byproduct in this computation. And if we otherwise, we would have to compute it using this formula, as in the oil drilling example that I presented to you last week. Okay, so to sum up this whole chapter on making decisions of static problems, first of all, decision theory was a combination of probability theory and utility theory. As you've seen, we always had to multiply the probabilities of the outcomes with the utility of the outcomes, and then sum over all possible outcomes. The utility theory shows that an agent with consistent preferences. So if all these axioms are preferential, or these axioms of how have we named this again? Axioms of, I forgot the exact terminology, sorry. So I go back to the slide here. So if axioms of utility theory are all valid, then as a consequence, we could obtain a utility. So that always when the utility is higher of A than B, then A is preferential over B. So this is equivalent. And if the utilities are the same, you're indifferent. And also we were able to compute utilities of lotteries instead of prices as well. Okay, and then of course, a rational agent selects actions that maximize the expected utility. So we've always done this in this lecture. We also looked at stochastic dominance, which is important if you have several attributes, and then you can make a decision on what is better in a stochastic sense. And we have looked at decision trees and decision networks, where decision trees is more straightforward and easier to understand, but they grow exponentially with the number of decisions. And decision networks, a more compact way, similarly as using Bayesian networks as compared to a full-fledged joint probability table. And the value of information has been computed to support a decision for whether we should gather additional information or not. Like in the car buying example, we can already compute, okay, how much are we willing to pay so that we have a benefit of this additional information, and when is it not worth obtaining this additional information. Good. That's all regarding rational decisions of static problems. So somebody wrote, buying a car that is faulty with 50% probability without doing a checkup does not really feel rational. That's correct, but you have to look at numbers that were given. I mean, so the thing is that you have, if you don't buy a car at all, you have really bad numbers, no matter whether it's a good or bad car. And even if you buy a bad car, it's like, how can I say, the negative utility is not much worse than not buying a car at all. And if you buy a car, it's really very high. So that because of this kind of mechanics, it's like, yeah, it's better. And also the checkup is quite expensive compared to what the value of having a car, like how can I say? I mean, the price of the car is actually nowhere written, but like no matter how expensive the car is, it is for that person much better to buy the car, because if it's not a lemon, it's a really high positive utility. You can also play around with the numbers, and let's say if the probability of a lemon is really high, then of course the value of checkout is increasing, for instance. You can just play around with the numbers, and if you like, you can also play around with the numbers and send us a new set of values such that checkout is worth it. But we took this example from another lecture, and the nice thing about this example is that it's a little bit surprising, which also shows you that intuition is not always your best friend. So if you always have examples where the outcome is as we expect, it's also a little bit boring. Okay, so let's have our 5-minute break, and let's continue at 5:15 with the new topic. So I already bring up the new slides, and I personally like the next lecture quite a bit because the results are very powerful and rather easy to explain. So I think this is a really nice lecture, the next one. Welcome back. Now what we're going to do is we are going to make decisions over time. And before, as I said, we looked at static problems. And if you have this problem that you are making decisions over time in a probabilistic setting, and you can measure the state exactly, then you end up at a Markov decision process, which is a standard concept and this is also the basis for reinforcement learning. And also in the next lecture, we will discuss reinforcement learning and use the results from this lecture. And there are basically two ways of solving Markov decision processes. One of them is value iteration and the other one is policy iteration. And that's it. So this lecture is really easily or simply structured. And as I said, I think it's very interesting. The first thing is that we have two different types of Markov decision processes, or the standard Markov decision process and also partially observable Markov decision processes, which can also handle the case that you do not that you're not able to know in which state you are. And however, POMDPs, as they are abbreviated, are removed from this lecture. So we constantly had this issue that we had too much content in this lecture. So this is now removed. And as I mentioned already, next year we will have not a 3+1, but a 3+2 lecture. So we will have more time, and then maybe this will be reintroduced or not. We will have to see. Nevertheless, for those who are interested in POMDPs, the slides that used to be in the lecture are also available in Moodle, but they're not relevant for the exam. You should also understand as a learning outcome the concept of an optimal policy and how it differs from an optimal sequence. So when we looked at search problems, we only looked at optimal sequences. And now we're looking at optimal policies, and I will explain to you why this is important. You can create utility functions of state sequences for finite and infinite time horizons. Because now we don't have the utility of a specific outcome, but of infinite sequences. Of course, we have to think how to compute them in a way that such that we obtain a finite value. And you understand, you know and understand the Bellman principle of optimality. Some of you might already know this. For instance, if you know how Dijkstra's algorithm works, then you might have already come across the Bellman principle of optimality. And you can create and evaluate Bellman equations for a given stochastic optimization problem. And you can solve these equations either using value iteration or policy iteration, which are both rather easy to perform. So the algorithms to solve this problem are surprisingly easy. Okay. So in contrast to the previous lecture, now we focus on dynamic environments. So as you remember, for static environments without actions, we use Bayesian networks. For dynamic environments without actions, we looked at hidden Markov models. Static environments with action, we just looked at decision networks today. And now we're looking at Markov decision processes, which combines dynamic environments with action taking or action making. Okay. Before we continue, we can now talk also about different variations of Markov models. So if you remember, if you have no action, but you can measure the state, then you had a Markov chain. If you had no action and were not able to measure the state, then you had a hidden Markov model. And now today we're looking at the cases that we can control the state transition, so we can take actions. And then if the state is fully observable, we have Markov decision processes. And if the state is not fully observable, we have this partially observable Markov decision processes, which are excluded now from this lecture. Okay. Just as another overview, this overview is kind of zoomed in from this overview. So where we just look at the different Markov models. Okay, so this is our example or our running example for this lecture. So we have a robot on a floor. So there's just this part here which the robot cannot enter. Maybe the elevator shaft is here. Then there's maybe a staircase which we shouldn't enter because the robot will fall down. And this would be the room that we want to reach. So there is something to pick up or so. So here we get a reward of +1, and this is a reward of -1. And the robot is not perfect. Some people could hit the robot, or there could be things lying around on the floor, so that if you tell the robot to go straight, it only goes straight with 80% probability and would go left or right with 10% probability. The same holds if you go left, then it would only go left with 80% probability and with remaining 10% up and down, for instance. So that is the transition model. The probability of the next state given the current state and the action is based on these probabilities here. And then you have this reward function, which tells you that when you reach one of the terminal states, you have a plus or -1 reward. And terminal state means that you solved, or the time stops, or the sequence of states stops, and the problem is kind of solved. Also, it would be solved if you end up in this -1, but it would be solved in a not so satisfying way. And for each step costs 0.04. So you would like to reach the +1 region in as few steps as possible. And the reward function here in this case just depends on states, not on actions. So we have a special case, it just depends on S, but there can be rewards depending on S and A, and there can be rewards depending on S, A, and the next state. Last year, we just looked at the case in this lecture of RS, which simplifies the formulas a little bit. So this year we are looking at a more general case. So some formulas are a little bit more complicated, but the benefit is that we can use these formulas directly for lecture 13, while in lecture 13 last year, we also had to then derive the case, the general case. So overall, we could simplify the lecture using this, and however, in the exercise, this RS case is still used in some exercises because you have to calculate less than, so the formulas is simpler. And as I said, we assume the environment is fully observable, so we know the state. If it's not, then you have a partially observable Markov decision process, or POMDP. Okay, so how is the Markov decision process now formally defined? So usually it's defined by a 5-tuple, where we start with the set of states S. In our case, in the example, this would be the tiles that we can reach with the robot. The set of actions would have been to go up, down, left, or right. P are the probabilities. The transition probabilities are the rewards. So these were -0.04 for each step, and +1 for reaching this good tile, and -1 for reaching the bad tile. And then additionally, we have this gamma, which is a discount factor. So just remember that this is a discount factor. What it means, I will show you later on. So it's just a repetition of what I said. And now we can start solving these Markov decision processes. So in search, the aim was to find an optimal sequence of inputs that led to an optimal sequence of states. In Markov decision processes, we cannot do this anymore, and we have to find an optimal policy. So given Given this problem, why can I not just use, let's say, A-star search or breadth first search to find an optimal sequence of inputs or actions? Why is it not working for this example? I mean, it looks like it would still work. So what would be, I mean, what would be a good sequence of actions? Yeah, we don't know the next state 100%. Right, that's the problem. So the thing is, a good sequence would be up, up, right, right, right. Okay, so let's assume we go up, but then with 10%, we don't go up, but we go left. And left means we stay where we are because there's a wall. So then we have up, up, right, right, right. So we would go up, up. The first up, we would stay here. The second up, we would go here. And then right, right, right. So we would hit this wall 3 times, and then we would stay here. And then this would not be an optimal action sequence. So what we have to do now is that we have to always make the next action based on the state we're in. So if you're in this state, the best action is to go up. In this state, the best action is to go up. If we don't reach this next state and we stay here, then we take up as a next decision again. And this way we can still reach efficiently the goal, although the outcome of the actions are uncertain. Okay. Okay, again, we want to maximize the expected utility. And for this penalty that is given, this would be the optimal policy. So in this state, we go up, here we go left, here we go up. So for instance, we don't go up here, because if you go up, there's quite a good chance that we end up in this -1 area, or this -1 tile. It's better to make this extra detour, because then you have a high likelihood of ending in +1 and a small of -1. And the extra detour isn't that bad because the costs for each step are quite low compared to the rewards in the terminal states. So then let's start with the first tweetback question. So this is the optimal policy. Would the optimal policy change if the cost for each step would change? So this is a rather simple question as a warm-up question. If you don't know, if you don't have the link, look at the first, go up the chat to the very first item, and then you see the link. Or somebody posted it again. So it's a yes or no question, which should be rather easy.
Yeah, so for now, I see over 90% chooses yes.
Okay, yeah, that's correct. Of course, this depends. And how does it depend? This is the next question. So you have 2 optimal policies. So on the left, you see the optimal policy for a cost of 0.04. And on the right, we would like to know whether the costs are 0.09 or 0.02. So whether A or B is the correct answer. So it seems that people are still busy voting, or the question is missing in the tweetback.
Now around 70% chooses A.
Okay, and A is correct. Why? Because you see A is, sorry, the new policy on the right is a little bit more aggressive, right? So instead of taking this detour, you in a more straightforward way, you try to go up to the +1 room or tile, whatever you call it. And the only reason why you would do a more direct approach why you would follow more direct approach is because the costs for each action would increase. So that's why here, this has to be the case with higher costs. And you can also see that given certain intervals of the reward, a certain policy is optimal. So if the cost for each step is extremely high, then it's even best to go directly into this -1 room, because when we enter this terminal state, the problem stops and we don't continue. So there will be no more steps. And if, of course, the costs for one step are higher, are greater than the punishment of ending in the wrong room, then it's better to really directly go into this bad room. So now if this is, for instance, a case where, let me just check. Yeah, where the reward is, the costs are less. And that is a case that we have seen on the previous slide, where we have still a quite direct approach, but we don't on purpose go into -1. We still want to go into +1, but we are taking the route that passes this -1 room. And this is then the case that we have seen at the beginning. Here we take the detour because then the chance of getting into +1 is higher and the costs are not so high. So this is fine. And if the costs are even less, for instance, here left of the -1 tile, we just want to hit the elevator, because then we have a chance of going up or down, but the chance of going to -1 would be 0 in this case. And also here, we try to go away from -1 as much as possible by going down instead of going left, because if we go left, there's still a chance of ending up in -1. Okay. These Markov decision processes are used almost everywhere. This is a non-exhaustive list, but it's used in agriculture, like how to best water plants, how to best drive around with a robot and so on to harvest things, for water resources, inspection, maintenance, repair, purchasing, inventory, production, finance, investment, how to optimally handle queues, sales promotion, motor insurance claims, overbooking in airplanes or hotels, epidemics, sports, patient admission, design of experience. By the way, epidemics was before the corona epidemic, so we haven't changed this slide. Okay. So the thing we have to discuss first is, what is the utility of a state sequence? Because we didn't have this problem. We just looked at the utility of a given outcome, but we didn't have a sequence of states in the previous lecture. So first of all, we assume that we have a stationary preference on sequences, meaning that if we make some decision R, if we have some reward R at the beginning, and then we have R0, R1, and so on, and we would prefer this sequence over this sequence, where the first reward is the same, but the other rewards are different. If that's the case, then this should also hold when the first reward is gone and we only have the reward from 0 up to infinity and the other rewards from 0 up to infinity. So it means essentially that if I make a first decision, maybe the decision is, or I get the first reward, and this reward, no matter how high it is, should have no influence on the remaining reward sequences. So if the remaining one is preferred, the left one is preferred, then this remains preferred if the first reward is not there anymore. And that applies to almost all real world examples. So I couldn't think of immediately of a problem where this would not hold. That you could probably construct something, but it would be quite odd. Okay. So now there are two ways of combining these rewards. One is we just sum all the rewards, and the other one is we have a discounted sum. And you can immediately see, and the discount factor is between 0 and 1. You can immediately see if you have an infinite reward sequence, the first one doesn't work, because if you add up all the rewards, this would go to infinity. However, here, the first reward is taken as it is, and then we multiply it with this discount factor, and then the further the reward is in the future, the more heavily this is discounted. So 100 steps in the future, it would be gamma to the power of 100 times the reward. And then you can imagine, of course, by bounding the maximum reward, this becomes a geometric sequence, which is, although the sequence is infinite, this is a this will because of the gamma value, this will become a finite value. Okay, we will discuss these different cases in a minute. So what we will do is, so this is the main trick of the whole lecture. We will now say the utility of the state we're in now is the expected discounted sum of rewards, assuming optimal decisions from this state onwards. So let's say we are in a certain state, and let's look at this room example again, or this robot example. Let's say we're in this state, and now we take the optimal policy, and we want to know what is the reward, the expected utility that we get following this optimal policy. And this the sum of the rewards that you get following this policy is then the utility of that state. So the state you start in is, or the utility of the state you start in is then expected utility when you start in the state, given the optimal policy until the problem is terminated. Or if it's an infinite duration, then for this infinite duration. Okay, and this can be written as follows. And this, if you don't immediately understand this formula, we will derive this formula in more detail when we derive the formula for utility. So this returns the optimal policy. So the optimal policy of a state is then the best action which maximizes the expected utility. So what is the expected utility? And also this aspect will be discussed in more detail later on. Is the current reward that we get plus gamma times the reward that we will expect for the remaining time. And because we already defined the utility of a state as the expected sum of rewards following a certain policy, this means that's the first step plus all other steps. That's the reward of all remaining steps, and that's the reward of the first step. And of course, we have to weigh these rewards with the probability of entering this next state as prime, because this depends. This has then because the reward and the remaining rewards depend on the next state. And we have to, of course, consider all cases. So as in the previous lecture, we multiply the probabilities with the utilities and sum this over all possible outcomes. And then we choose the action that maximizes this expected utility. So now in each of the states, we have already written the sum of rewards that we expect when we start in the state. So what we now have to do is we just have to check, okay, if we go up, we go with 80% in this state, and with 10% we stay in this state, and with 10% we go here. And then we get the rewards and add the utilities, and we check this for up, left, right, and down. And then we choose the action which is best. And this best action is then this optimal policy that you see here. So this is shown on the next slide for this exact numerical example. So for going up, if you're in square 3.1, which is this square here, then you have a 80% chance of when you go up of ending up here. So then the reward is minus 0.04, which is the current reward, plus the 0.660, which is the remaining rewards, plus 10% of going here. So you get this reward plus the cost for going there, plus 10% of right, which is the immediate reward, which is negative, so it's a cost, plus the remaining reward that you expect. And you do this for up, left, down, and right. And then you see for this square, the best action with the highest utility is left. And that's also why left is the arrow here. And then you do this for all the squares, and then you get the optimal policy for each each state. Okay, so now let's talk about this infinite horizons. So if you the first solution is that you have a finite horizon. So you have a you say, okay, the horizon is fixed. Our problem just lasts for 20 steps. The problem then is that you always stop after 20 steps, is that the policy, which is optimal, doesn't only depend on the state, but also on the remaining time. And that makes things quite complicated. So this is something that can be done, but it's not much favored in most applications. The second case is you have an absorbing state, like we have in our case. You have this terminal state where you get +1 or -1. And if the probability of ending up in the one of these terminal states becomes 1, if time goes to infinity, then you also have a finite a finite utility, even though you don't have a discount factor. And then the next case is the discount factor case, with gamma has to be between 0 and 1. And we assume that the rewards are finite, so there exists a maximum reward. And now what you can do is you can, when you add up all these rewards, you compute an upper bound by replacing all the individual rewards with the maximum possible reward. This you can factor out, and then you have an R max times the sum from t equals 0 to infinity of gamma to the power of t, which is a geometric series. And the sum of this, if gamma is less than 1, is 1 over 1 minus gamma, right? Which is this here, multiplied with R max. So this is then a maximum possible value, and this is a finite value. And this discounting is usually done. So in most applications, people use this discounting because it's very versatile. It leads to these stationary policies, and it's very easy to compute with those. And the last one is, instead of maximizing over all the rewards, you can just maximize over the average reward per time step. So then an infinite sequence can still be handled by comparing average rewards. However, handling those is not part of this lecture. It also makes things more complicated, so this is excluded. Okay. So now, I mean, how to compute this optimal policy? This was introduced quite abruptly. So now what we're going to do is and also what you need for this optimal policy are the utilities. So we will now introduce how to compute these utilities using the Bellman principle. Okay, so the Bellman principle of optimality simply states that an optimal policy has the property that if you go to an intermediate state of this optimal policy, then if you start there, then from there onwards to the goal, the optimal solution is part of the optimal solution of the entire problem. So in other words, let's say the pandemic is over and you want to go to a physical party in Olympiazentrum. So for instance, you want to go to Oli Disco, and you right now in our lecture, which would be in presence if the pandemic would be over, then you would take probably the subway and go to Studentenstadt, and from Studentenstadt you change. Yeah, wait a second. Yeah, then from there you take the bus. Yes, so I think you take the bus and then go to Olympiazentrum. I think that's the fastest way still. And then because you have to change in Studentenstadt, if you are in Studentenstadt already and you want to have the optimal solution to go to Olympiazentrum, then this optimal solution, of course, is part of the optimal solution to go from Garching to Olympiazentrum. So this is kind of it's very intuitive. It's just, it's simple and intuitive, but it's a very powerful principle. So if you want to have the best decision, you first take the best first action, and afterwards you take the best remaining actions. And that's also the same principle that we used for finding the most likely sequence in hidden Markov model. So there we already used basically the Bellman principle. So now let's look at a simple example. So you have two actions on and off. So now you're in state S1, and if you perform action on with 10%, you end up in state S3, with 50% in S4, and with 40% chance in S7. And from there on, you would again take the remaining best actions. And the other option is you have used the action off, and then you're with 70% in S3 and with 30% in S6, and then again, you continue with the best actions. So the utility of the state then would be the immediate reward of the state where you're in right now, plus the utility of the state that you reach, because the utility of the state that you reach subsumes, according to the definition of the utility of a state, all next actions. And you have to first look at the case that you take action on. So for action on, you have 10% of ending in S3, 50% of ending in S4, and 40% of ending in S7. And then this value is compared to the other action, which is off, which produces this kind of utility values. And then the action that is best is then the optimal, or the utility that is best is then the utility of S1. And of course, the action that is best is then defines the optimal policy. Okay, so this brings us to this formula. I just will finish this slide and next one, and because these belong kind of together. So here we have then the probabilities of ending in the next states as prime, and we multiply this with the instantaneous reward plus the future reward. So current reward plus future rewards, and we take the best action for the current reward. This is exactly this principle. So best first action and then best remaining actions. And of course, we want to optimize the utility. So that's why we're taking the action that provides us with the best utility. So again, if you use our 4x3 world example, and now if you're in state 1-1, then again, you have 80% of going to state 1-2 if you have the action up, and 10% for the sides, the same for left, down, and right. And if you compute the utilities for each action, then you see that up is the best action, and the utility that you obtain is also then the utility that we're using. The question now is, the problem is we need the utilities to compute the utilities, as you've seen. So this is kind of a hen and egg problem. So we will discuss how we solve this problem tomorrow. I would just like to, this is the last slide for today, show you another way of coming up with this formula, which is maybe even more intuitive. So if you look just at the one, if the agent lives for one time step, then you just get the immediate reward, and you want to take the action such that the immediate reward is maximized. And again, of course, here you already have to consider the probabilities of ending up in different states, but this is a formula we can easily agree on that this is a correct formula. If the agent lives for just 2 time steps, you get the immediate rewards plus the rewards if the agent lives for 1 time step. So U1 means the utility that you obtain for 1 time step. And then you have the utility for 2 time steps. And if you want to have the utility for I steps, then you have the immediate reward plus the reward for all the time steps following from I minus 1 up to 1. And of course, if I goes to infinity, then this converges and the index is removed. So this index is removed and this index is removed, and then you end up with this formula. And this will also be the main formula that we use for value iteration, which we'll discuss tomorrow. So we can just start with a random value and iterate and then converge to the true values for the true utilities of the states. Okay. So we'll look at this tomorrow, and we will also prove that this converges. And then we already have the value iteration, and then we just look at the alternative, the policy iteration, which is very similar. And then we can already start possibly, I mean, I think with very high probability already with learning approaches tomorrow. So yeah, I said initially tomorrow we'll have a double exercise, but today I talked with Josephine and she said that she just needs 45 minutes. So I think on Moodle it's correctly announced. So I think I made a mistake saying that tomorrow is already the double exercise, but then the other remaining exercises, so then tomorrow is still exercise and lecture, and all other remaining Fridays will only be exercises. Okay. So thanks for joining. I wish you a nice evening. And tomorrow will be interesting because this approach is really so easy and very powerful. Okay, so see you tomorrow. Bye.